Alright guys, this is our next lesson in the unit on derivative. We're moving on to the next lesson, lesson 3.3. We are going to closely look at what it means for a function to be differentiable, and then we're going to go ahead and start with the power rule. And a lot of you are waiting for this power rule because it makes it a lot easier for us to take the derivative instead of using the definitions. So just a few quick goals for us. In this lesson, I want you to be able to recognize graphically when a function doesn't have a derivative. Know how to analyze the derivative at a point given a graph. That means that you're able to look at the graph and say, oh, the derivative, the slope of the tangent line is a half, and so on and so forth. Given a graph, given the graph of the function, you should be able to sketch the graph of the derivative and also vice versa. Alright? Cool. Alright, so let's begin. Remember that we say that a function is differentiable if the derivative exists. So a function is considered to be differentiable if the derivative exists for every point on that domain. Now, there are some functions where it is non-differentiable or derivative does not exist. Those type of functions are continuous. It's just that the derivative at some specific point do not exist. One type of function is what we call a cusps, and these are functions that have like fractional exponents. That's an example of a cusp. This sharp point does not have a derivative. A more common one is like when the function has a corner. Usually the type of function with a corner is the absolute value function. So the derivative will not exist at that point, but it will exist everywhere else. A last type of function where it is non-differentiable is a type of function that has a vertical tangent line. So the graph kind of turns and it comes to like a stall there, and then it kind of flattens out. So any graph with a vertical tangent line is also non-differentiable. And of course, any graph that has a point of discontinuity are also non-differentiable. Okay, a jump, a removable, infinite, and oscillating, those are also non-differentiable. Alright, so if a function is differentiable, then we know for sure that the function must be continuous. Because in order for a function to be differentiable, it can't have any corner or sharp turns. It has to be smooth. Okay, so any differentiable function has to be smooth, and it cannot be discontinuous. That's why we say that differentiability implies continuity. There's no sharp turn, and there's no discontinuous in the graph, and that's what makes a function differentiable. However, continuity does not imply differentiability. Just because a function is continuous, it doesn't mean that the function is differentiable everywhere. For example, this is an example of a function that's continuous, but it is not differentiable at that point, and therefore we say that continuity does not imply differentiability. Awesome. Let's turn to the back now. As we continue to move forward in Unit 2, Chapter 3, we always review concepts that we have encountered in the past so that we don't lose those concepts. So keep in mind that when a function is increasing, so here's an example of a function that's increasing. So the highlighted part is where the function is increasing. The slope on that part is positive. If you were to measure the level of incline for that line right there, then the level of incline is positive, right? It's going to be a positive number. It might be like a half, but it's positive. If the function is decreasing, so here's where the function is decreasing, notice that the slope value, the slope value is negative, right? And wherever the function makes a turn, I don't know if you can see the turn, but here's where the function turn, all right? The slope is 0. So f prime, where the function term equals to 0. All right? Awesome. So, going back to the ability to sketch the derivative. How can I sketch the derivative of, sketch this? Given a function, sketch the derivative. All right? First, I'm going to have you try to match the function to its derivative and see which one kind of correlate with the one on the first column. The way how I would do this is I first pick a function. So let's do the first one. And I first identify where the slope of that function equals to 0. All right? So I look at this function and I know that the function turns at, so it turns where? It turns at x equals to 0, right? This is where the function turns. X equals to 0, the function turns. So I know that the derivative at x equals to 0 is 0. So why don't we just call, so f at 0 is 0, because that's where the function turns. So when x equals to 0, f at 0 is 0. So the derivative will be right there. Okay. Now if you look at the graph of the derivative, there are two graphs that has a point at the origin. That is the first one and the last one. All right. So for sure, B is not going to be an answer to question number 1. All right. Now, why don't we analyze why don't we analyze where the function is decreasing? All right. So the function is decreasing. The function is decreasing here. All right. And if the function is decreasing there, when the function is decreasing, the slope is going to be negative, right? It's going to have negative slope. It's going to have a really big negative here. Okay, so at like maybe about -2.5, it's going to have a really big negative number, and then it kind of level out here. So it's going to have a really big negative number, and it levels out. Okay, and and the slope equals to 0 at 0. So on this portion, this is the graph of the derivative. And as you can see, on this portion, the slope is going to be positive, right? The slope is going to be positive. So it's going to have, at 2, it's going to be a big positive. So maybe start, I don't know, right up here for really big. And then the slope goes like maybe -5, -4, -3, -2, -1, and 0. Okay, so line should look like that, which that's the graph of the derivative. So it matches up with option C. See, so we go, oh, C, choice C. All right, you can go from function to pick the right derivative. All right, now what I'm going to do next is I'm going to kind of reverse the order. I'm going to look at the derivative and I'm going to see which function matches up with that derivative. Okay, let's do this one first. All right, so I look at the derivative and I know that the derivative is positive for any x value to the left of -1. So we know that f prime is a positive number. What does that tell us? It tells us that the function is increasing from -infinity up to -1. The function is increasing. So if you look at the last two functions, can you tell me which two function is increasing on the domain of -infinity to -1? And if you look carefully, they are both increasing, right? They're both increasing. All right, well, that kind of helped. That kind of helped a little bit, but not really, right? Okay, well, let's take a look at where else it's increasing. Well, the function, the original function, because the slope from -1 to infinity is also positive, takes on positive value. The slope is taking on positive value, right? That means that the graph of the function should also be increasing from 1 to infinity. And if we look carefully from 1 to infinity, the only graph that's increasing is this guy. So guess what? B is the right option. Okay, so you can analyze the graph to get the derivative. You can analyze the derivative to get the graph. Right? I'll go back to maybe analyze. Well, yeah, let's go back to analyze the derivative to get the graph. How about that? So look at this portion. Okay, or maybe look at this portion. Look at these points. Look at these points. These are the points where the graph has a slope of 0. In other words, those are the point where the graph turns. As you can see, the graph turns. See? The graph turns at -1, so it has a slope of 0. The graph also turns at 0. Okay, so these are the point. So the derivative at -1 equals to 0. The derivative at 0 is equal to 0, right? The derivative at 1 is equal to 0 because the graph of the derivative is touching this x-axis, so that's why they take on 0. And if we look closely, these are the point where the graph, the original graph, makes a turn. That's why the derivative equals to 0. So we go back over here, and you can kind of see that the graph does turn at those points, right? So that's one of the ways to kind of match those graphs up. So guess what? A is this guy. Okay, that's A. All right. What's the next part of the lesson? And then we'll finish the lesson.